All right, section 9.3. This time we're talking about geometric sequences and series. Series, by the way, just means you're adding the terms. You're adding up several terms while starting at the beginning and adding to a certain point. So series, you're adding. Sequence means you're just listing them. And we'll see what makes one geometric. So we had arithmetic before, now we have geometric. We're going to determine if a sequence is geometric. Find the formula for a geometric series, like a sub n equals, and we want a formula, preferably a formula that when we put in n, we will calculate the value of a sub n. Find the sum of a geometric sequence. I kind of would like this better if it said find the sum of a geometric series. Series is what we call it when we add the terms of a sequence. We're going to determine whether a geometric sequence converges or diverges, which will make sense when we get there. Solve annuity problems. I crossed that out. We don't cover that. So you need two measurements to have a geometric sequence. We call the first term A1 or A, and we call R. Now, only geometric sequences have an R. R is called the common ratio, and it is calculated formally by any term divided by its previous term. I say formally it's calculated that way. In practice, it's very rarely calculated that way. You just kind of see it by inspection, by reasoning. But if you are ever in a pinch and you want to calculate it, it's any term divided by the previous term. If that's common, if that doesn't change in the list of the sequence, then you have an R, which is a common ratio. If you have a common ratio, it's a geometric series. All right, so a lot easier to see here. So the thing that's visible is the first term. A1 is 3. The thing that's invisible is the common ratio. Now the common ratio is what I'm multiplying by every time I want, or every time I get a new number, a new term. And I think that's probably a superior way of thinking of the common ratio. You just say, oh, look, I'm multiplying by 4, and I'm multiplying by 4. I multiply by 4 to get the next term. I like doing that more than the formal one, which is to pick a term and divide by the previous term. I don't know, it just feels like I'm looking backwards when I do that. But if you were going to use your calculator, try it. Take a term, divide by the previous term. The author did that for several examples. But any term divided by its previous term is 4. Any term divided by its previous term is 4. 12 divided by 3 is 4. So since I get 4 every time, the common ratio is 4. And that means that I could find the next term by multiplying by 4. So, by the way, if I write that down, R equals 4. This, in mathematical terms, is a perfect description of this sequence. In fact, it's a better description than just giving you the numbers. This is a list of numbers, but this is a way of generating not just this list, but any list as long as you want, because we know that we'd start with 3 and we'd multiply by 4 to get to the next term. And if I know that, I multiply by 4 every time. And I know that because it's R. You don't have an R unless you're a sequence that's multiplying by a certain number. I know that if R is 4, I multiply by 4 every time. And so I could reconstruct this list with just these two numbers. So a lot of formulas will be based on knowing these two numbers. You need to know these numbers to do pretty much anything with a geometric sequence that we're going to be asked. I went through this earlier, and I don't know. This one has two ways of looking at it. They give us the very formal sequence, and notice what they didn't give us. They didn't give us A, and they didn't give us R. Now, if they had just told us that, or given us a list so we could find A and R ourselves, that would be great. But they gave us the formula. And that does make this problem, I suppose, more formal than most of the problems we'll come across. Because, in practice, most of the time you're just given the list. You're very, of actual numbers where you can actually look at them. Or you're given A and R, but they chose to do it this way. So we have several choices. One choice is to just fill this up, just to list it. In fact, I would always recommend doing that. If n is 1, I have 3 to the minus 2. If n is 2, I have 3 to the minus 4. If n is 3, it's 3 to the minus 6. And doing this gives me a feel for the list of numbers. I'll do one more step. I could do even more steps after this, but I think this tells me everything I need to know. On a very informal basis, I can tell what I'm multiplying by to go from one to the other. The numerator doesn't change, so I'm multiplying by the fraction 1 on the top, but the denominator each time increases by 3 squared. So my analysis, just by making the list and looking at it, is R is 1 over 9, or 3 squared. 1 over 3 squared. And the first term also happens to be 1 over 9. So this sequence is better described by the first term in the common ratio, but the author chose to go to use more formal methods. So the author said, all right, this is the formula for A sub n that was given to us, and the previous term would be, I would replace n with n minus 1, and so what the author is going to do is take this term and put it on top of a fraction, and take the previous term and put it in the denominator. Remember, the formal formula for common ratio is exactly that. A sub n divided by A sub n minus 1 equals R. So the author is using that formula. Well, here it is. And the other worked it out to be 1 over 9, which is kind of what we knew it was going to be just by looking at the list of numbers. So some of these problems have a very intuitive way of seeing them, kind of like we were using in section 9.1, but the author is saying, you know what, we could do more than just use intuition. We could use our definition of R, and that will also give us the certain numbers. Well, our job really isn't just to find the common ratio, but they did it again. The thing is, these common ratio questions are so easy when you have the list of numbers in front of you, and there's nothing stopping you from making that list of numbers. So you'll never have a problem this complicated unless you make it this complicated. So I'm seeing what the author did, but what I'm saying is, you could say, well, if n was 1, it would be 2 times 3 to the 1, 2 times 3 to the 2, 2 times 3 squared, 2 times 3 cubed, 2 times 3 to the 4th. This is 6. This is 9 times 2, 18. This is 27 times 2, 54. 81 times 2, 162. What am I multiplying by? That's the question. Well, you're multiplying by 3. And so this idea of common ratio, pretty straightforward concept, unless you intentionally make it more formulaic or more complicated. We don't have too many questions like this, but I just wanted to warn you that you don't have to use the complicated way when, what I say, make invisible things visible. And if you make invisible things visible, then a lot of things become much easier. It's a little harder when you're dealing in more algebraic notation here. All right, so I said the most important thing to make something visible in a geometric sequence is to know A and to know R. And if you know that, or A1 and R, if you know that, you know everything about the sequence, including a formula for the nth term. The formula for the nth term is A sub n equals A1, the first term, times raised to, times R to the n minus 1. So this is a formula you just want to have, available in your mind. And let's see how it works. So we had lists of numbers like these back in 9.1. It's not based on adding, it's based on multiplying by a certain thing. And I actually like fractions in a case like this. I multiply the numerator by 2, and I multiply the denominator by 3. And if they tell me it's geometric, then I really don't have to verify that anywhere else. I just know it. I am multiplying by 2 over 3. Now, I could use the formula, this 2 divided by that 3, any term divided by the previous term, which is, in this case, a pretty good way to do it. But you need R, and you need the first term. And then you also need the formula, so we'll do that. All right, after we find the formula, we'll find the 9th term. And the 9th term, I guess I could do that by just continuing this list, but you already know my opinion of that. If the list is very long, I might not get the right answer. Recursive formula. All right, we'll do all of these. This is the formula we're substituting into. First term is 3, R is 2/3, and we just like to leave it that way. It's not something that we need to try to work with. Certainly don't try to mess with the n minus 1. I mean, there are exponent rules you could do to simplify this, but don't oversimplify it. In this case, we don't mind having an n minus 1. So in other words, that's the answer, just from substituting these values in. Does the formula work? Yeah. Let's say you wanted to test this formula for n equals 3. Do you remember what the third term in the sequence was? 4/3. If I tested this and said n equals 3, I'd get 3 to the 2/3, times 2/3 to the 3 minus 1. That would be 3 2/3 squared. 3 times 2/3 times 2/3. And what would survive is, well, 4 over 3. And I was just verifying that the formula does give me 4 over 3 when I substitute n equals 3. So, what's the 9th term? Well, it's 3 times 2/3 to the 9 minus 1, or 3 times 2/3 to the 8. They didn't bother writing it as a fraction, just kind of calculated it. but 3 times 2/3 to the 8 would be the 9th term of that sequence, ninth number in the list. All right, so recursive formula. Recursive formula is probably the most intuitive thing we could do here. It's, let's start the list again. Remember, it was 3, 2, and then, I already forgot, 4 over 3. All right, so if I have two terms here, a sub n minus 1 and a sub n, how do I find a sub n? That's right, I multiply it by r, which is 2/3. Just kind of picture it in the stream of this list. And what does that mean in an equation? Well, in an equation, it means a sub n equals 2/3 times the previous term. That's this formula. A sub n equals 2/3 times a sub n minus 1. And what started it all? Well, what started it all was a sub 1. So when they ask for a recursive formula, that's what they're looking for. The first term and then a formula for a sub n based on the previous term. Now remember, we already did something better than that. This was finding a sub n based on n. If you don't understand how that's better, imagine using this crazy formula to find the 9th term. I said, oh, well, the 9th term, a sub 9, that's supposed to be a sub 9, is 2/3 times a sub 8. Well, what if I don't know a sub 8? Well, I'd have to find it. A sub 8 is 2/3 times, shouldn't be, okay. A sub 7. So I'm just kind of chasing this all the way down. I can't find a sub 9 without a sub 8. I can't find a sub 8 without a sub 7. So while this is the answer to the question, what is the formula? What is the recursive formula? The superiority of this formula to answer questions, because, I should be saying this formula, because we're putting in n to find a sub n. You don't want a formula that you have to put in the previous term to find the next term, because that doesn't really help you when n is a number beyond the ones you know. Like if you know the first 4 terms of the sequence, yeah, using this to find the 5th term is okay. But if you know the first 4 terms of the sequence, using this to find the 100th term, would be a nightmare. All right, we're at that point where we want to find S sub n, and S sub n is the sum of the first n terms, just like it was with arithmetic sequences. All right, now there's a different formula though. So the formula for the sum of the first n terms, don't think we need this one specifically. That's just a restatement of this list. You know what it means to have the sum of the first n terms. It's the first term plus the second term, and they just kind of, gave us that whole list. There were some formulas that they're kind of, I guess, referencing here, which I'm going to seriously tell you not to worry about. But know this formula, know it in its alternative way of writing it with parentheses. This is the formula for S sub n, the sum of the first n terms of a sequence. It's the first term multiplied by 1 minus r to the n divided by 1 minus r. That might not look easy, but it's certainly better than adding a bunch of terms together. Let's look at what I mean by that. All right, not a fan of this particular example because it asks you to find the sum of the first n terms. Let's find an example where they ask you to find something a little more specific. I didn't. Okay. So I will shorten this. Let's say we wanted to find the sum. I mean, I'll talk about n terms in a minute, but let's say we just wanted to find the sum of the first 3 terms. Okay, I know we could do that without this formula, but that's actually the point. The sum of the first 3 terms, just using addition, 1/3 plus 2/3 plus 4/3 is 7/3, and that's the answer. Well, now I could have asked you to do more. I could have said find the sum of the first 40 terms. And you certainly wouldn't want to have done that for 2 reasons. One, we don't know the list of 40 terms, and it would just be a lot of work. But I could use the formula that they're using here, but remember what I'm doing. I'm changing this example to just finding the sum of the first 3 terms. So if I try to do that with a formula, this would be a 3, and that's the only change that I'd get. How would that change the reasoning? This would be 1 minus 8 over 1 minus 2, 1/3 times -7 over -1, which negatives would cancel, and I just get 7 over 2. And hopefully that looks familiar. That was the... Oh, man, 7 over 3. Oh, yeah, here it is. My 3 looked wacky. 1/3 times 7 would be 7 over 3. All right, so I have 7 over 3 both times, just by straightforward addition and by doing this. In a way, this problem was a little, I don't know, less complicated, at least in its format, because they didn't want us to find, the question I changed, they want us to find the formula for S sub n, and by asking you to do that, it's one less number to deal with. You didn't need to find the 3rd term, you just left the n in the formula, and they simplified it. But any question we're going to have, they'll pretty typically give you a number, like find S sub 3, and you can just do that directly. Find S sub 20, and you could do that directly. Or S sub 9 like we did in the previous one. All right, here's where geometric series get interesting, and that is we're sometimes asked to find the infinite sum. And that sometimes stumps some students. Actually, it stumped humanity and very brilliant thinkers for hundreds of years, where they were saying, well, if you're adding a bunch of positive numbers, wouldn't the sum just be infinite? And the answer is no, not always. All right. So the question is, what happens if you add an infinite number of terms in a sequence? Well, here's the rule. If it's geometric, it can't be arithmetic. If it's geometric, and the absolute value of r is less than 1, what that means is r is a number between -1 and 1, a fraction or a decimal, right? If that's true, then the sum of all of the terms in that sequence, all infinite terms in the sequence, is given by this fairly simple formula. The first term over 1 minus r. This is an amazing result. And we'll see what that means. All right, so they hid a geometric sequence here. Now it's not hiding. Here it is. 3, 3 over 2, 3 over 4, etc. Each time, just to make it, so we can see it, it's geometric, so we know that you're multiplying by 1/2. Hopefully you can see that. R equals 1/2. If you can't, you can use the more formal reasoning the author might have given. But Since r is less than 1, this converges, meaning I can apply this formula. By the way, the opposite of converging is diverging, and that would mean that most of the time the sum would just be infinite, or the individual entries would be infinite. And when I say infinite, I mean they just they grow without bounds. They just grow infinitely large. Here the terms are getting smaller and smaller. I'm dividing by 2 every time. So after not that many terms, I'm getting very small numbers. So 3 over 16, 3 over 32. After a while, the fractions will just get a lot smaller. So they'll get so small that the last, I don't know, after the, I don't know, maybe the first 20 terms or fewer than that, we're going to get very, very close to the infinite sum that this possesses. But there is an infinite sum, and it's going to be a fairly small number. It's not going to be like some outrageous number. Here it is. The sum of this entire sequence out to infinity is, remember the formula, a over 1 minus r. So the first term over 1 minus 1/2. Well, that's just 3 divided by 1/2, or 6. So this entire sequence has a length of 6. Now that might be kind of hard to see, and I'm going to, real quickly, explain why it's 6. So remember the first term was 3. What's the next term? 3 over 2. So that's half that distance. So if I add 3 over 2 to the 3 that I had, I'm right here, halfway to 6. What's the next thing I added? 3/4. We have to think about this. But if that's 3 over 2, this would also be 3 over 2. If I cut that in half, it's 3/4. So what's going on here is I'm always cutting this in half, 3/8. If I cut that in half, it's 3/16. Hopefully you get the idea that I'm just getting closer and closer, but I'm always adding half the distance to 6. What that means is 6 was a reasonable number for this infinite sum. There's no way that doing this, always adding half, adding half, adding half, would get me to 7, for example. If I just add halfway to 6, the sum is 6. The sum of all the pieces is going to be that number 6. So I just that illustration's not generally part of this course, but it just kind of helps you see that you really can have an infinite number of things as long as they're getting smaller, substantially smaller. You do have a limit, and the limit is the sum of all the terms. So I had said this, the sum of the first, 8 of them. There's the first, the second, the third, the fourth, fifth, Some of the first 8 of them is going to be very close to 6. So the sum of the first few terms usually approximates the infinite term as well, infinite sequence as well. All right, something that might be a little more familiar to you is repeating decimals. And so they're asking us to show that, well, this repeating decimal, 0.99999, 1.99 times equals 2, actually equals 2. So we take this sequence, we take the number and put it in a sequence. So look at the sequence. It starts with 1, and then we multiply by 0.9, we multiply by, well, let's look here. Every term after the 1, we're multiplying the top by 1, right? It's because it's not changing, and the bottom by 10. So we're multiplying by 1/10, which you might have noticed if you just look here. We're multiplying by 0.1 or 1/10. So R is 1/10. Now, this 1 is kind of an odd bit to this sequence. There's no way I can incorporate that into the series or the sequence, so we're just going to leave that leave that out, and just add all of these terms together. We'll add the 1 in later. So this is the question, essentially. They didn't really do anything here. But we do have to recognize that the first term is 9/10, and R is 1/10. That's really all we need. So to answer this question, I don't really see any point to doing all of this here, other than just to show you the notation. To answer the question, we want to take A1 and put it here in the formula, and we want to take R and put it here, 1 minus R. So hopefully you see it. We run that calculation and we get this is 1 plus 1, or 2. So we just showed, basically we just showed that 0.99999 equals 1, because this is the 0.999 written in terms of A and R, and then incorporated into this formula that gives us the infinite sum, and that equaled 1. This one here. The one that was given in the previous problem, because the problem started with 1.999, is there, and so that's why it equals 2. All right. Well, that was some pretty heavy stuff. Like I think I said it, things like this are still debated by people. You know, is 0.999 really equal to, repeating really equal to 1? And this is probably one of the more sound proofs that it is. People who haven't reached this level of math have a little trouble accepting that 0.9 repeating is actually equal to 1. But, if we believe our formulas, specifically this formula here, then we've just verified that 0.9 repeating is 1. There are others that, other things, but just remember that there is a argument going around there that where people use this formula for R that doesn't fit in the restriction that R has to be less than 1, and that does lead to some inconsistencies. So we believe this formula as long as R is less than 1. That's an important idea. If R were some other number, that would not, this formula would not hold. So I just thought I'd throw that out there for people who might have seen the arguments about that nature. But that's it. Section 9.3, the arithmetic, it's the, not arithmetic, the geometric sequence, and all of the things we can do with a geometric sequence. There it is. Geometric sequences and geometric series.